So we had to go through and look at how our alkenes would react under a different condition. So we're using radicals to force our alkenes to react, to get them to initiate and run through. Okay. One of the things that we added, I think, into the lab time, I think everybody else had left, is that when we look at our radicals, they're kind of obnoxious because the large part that drives radical reactions is concentration. Okay? And that concentration information is not embedded in our reactions. So when we look at a radical reaction, what we need to see is that ROOR, that is a big signifier that what we have is a radical initiator. I now have a radical. What is the most likely thing that radical encounters? Those of you that saw this know the answer. What is the answer? Careful. What molecule does it encounter? HBr. Okay. That radical will react with which atom of HBr? The bromine or the hydrogen? Hydrogen. Reacts with the hydrogen because what happens when we do our radical mechanism is that we end up generating our standard alcohol and a bromine radical. If we had reacted our radical initiator with the bromine instead of the hydrogen, we would have ended up with a hydrogen radical, not stable. Okay? So the bromine radical is more stable than our hydrogen radical, which is a good reason for it to form. It is also more stable than the oxygen radical. Why is the bromine radical more stable than both hydrogen and oxygen radicals? It's bigger. It can stabilize that unpaired electron a little bit better. Okay? We now still have a radical. That radical must be neutralized somehow. So it floats through solution until it encounters. Okay. We're hearing two different answers on this, which is kind of a good call. The correct answer is it encounters HBr. HBr is present in the highest concentration. And we go through and do the exact same reaction that we just did with the initial radical. What's the product? HBr and bromine radical. That reaction happens extremely frequently. Okay? Eventually, that bromine radical does encounter the alkene. That's what then cascades into our next effect. So we now have our bromine radical and our alkene. So our electron comes out, and one electron from that pi bond goes out to form the new sigma bond to our bromine. The other electron in that pi bond goes to the opposite carbon. Where do the electrons go? Okay, well, what dictates where the electrons go? Stability of the products. So if you don't know which, draw them both. So we can call this our red product. The other option, I'm drawing over the top of it, would be our blue product, that one word. So we'd have our red product or our blue product. Remember, we can't just get rid of the radical. Which of those is more stable? Why is the red radical more stable than the blue radical? It's tertiary. Why is a tertiary radical more stable? This comes back to what makes a radical unstable to begin with. It's missing electrons. Okay? So what's going to make it more stable? Give it more electrons. What's around a tertiary radical? More electrons than around a primary radical. Which means when we do the radical reaction, the product that is favored is our red one, and we don't have to worry about the blue one at all. Is this a final product? Why not? I don't quite that it needs to encounter another. Why does it need to encounter another HBr? Why is this? It's still a radical. It is still not stabilized. So it needs to continue to react. More than likely what it will encounter, just like with our bromine radical, it'll encounter HBr. Our radical from our carbon comes out, shares an electron, and an electron from our HBr comes out of that bond. Which one or which atom forms the bond to the carbon? The hydrogen or the bromine? Dead silence means, guess what you get to do? Draw them both. And I am watching you now. Draw them both. Because I'm not going to draw them both. I already know the answer. Okay, we've got our two possible skeletons coming out. If our radical comes out and reacts with the bromine, we will form the blue structure. What is missing in that blue structure? The bromine. We said the electrons coming out and reacting with the bromine. That bromine would need to go here. What would the other product be? A hydrogen radical. In the red case, the electron from our radical, our former alkene, comes out and reacts with the hydrogen, which means what is missing from, well, sort of missing from our structure? Show that hydrogen. It's technically implied in that, but let's go ahead and show the hydrogen. What would our other product be? Bromine radical. Which of these two products is more stable? The red, because the most reactive species in both of these is the radical. We can compare the radicals. The bromine radical is more stable than the hydrogen radical. Red product wins. Okay? So at the end of this whole big long reaction, that was a little weird, we end up putting the bromine out there. The net result is that we have done what? So net result means, look at that. Beginning, end. What was the net result? What type of reaction occurred? Addition. Can you add more to that? Radical addition. Okay? Because we went through a radical mechanism to do this. Why is this addition reaction a bit odd? If we change that reaction now, what would we expect the product to be? What did I change? There's no more radical initiator. What's the product if I react an alkene with HBr? It is still an addition reaction. Okay, we'd run under the acid-catalyzed addition reactions. Our hydrogen goes to the position that already has the most hydrogens. Okay. Where does the bromine go? The most substituted position. What is the difference between the blue product and the black product? Placement of the bromine. What we've done is what's referred to as a Markovnikov addition in blue, and what is unfortunately referred to as an anti-Markovnikov addition in black. Don't focus on the letters, okay, or the terms, because that really wasn't important to this. What was important is looking at the stability of each of those individual species all the way through, and that's how we get those answers. Not memorizing that it's Markovnikov and anti-Markovnikov. Okay? That guy's been long dead a long time. He doesn't need to hear his name anymore. Okay? What happens in the next reaction? What changes as we go from the top one to the next one down? I'll kind of accept just the radical initiator. I'd rather hear the what's missing. No HBr. So the radical initiator reacts. What happens? We now have our radical initiator. What does that initiator most likely encounter? Not another radical. Careful. The odds it encounters another radical is very, very slim. When we look at radical mechanisms, it's very rare to get radical-radical interactions. What is that radical most likely to encounter? The alkene, the pi bond. That is the only other thing present. In our first reaction, what it encountered was HBr, because HBr was present in high concentrations. HBr is not present here. The only thing it can encounter is the alkene. So it reacts, right, and it forms a bond. What would that product look like? Draw it out. what will end up happening is that radical will react with our pi bond to generate the most stable radical. You form the tertiary radical, the OR is now connected out there. Is this product stable? No. Okay, so it now needs to go back into solution and find something to react with. What is out there in solution for it to react? Another pi bond. It also has another radical out there. That is a possibility. But as we already kind of talked about, your radical concentrations are incredibly low. Radical-radical reactions very rarely happen. Okay? Which means we have to do this again with another pi bond. Do it. Counters another radical. I'm going to have to go through the bond. What's the result of this? I'll try and color code it even. Okay, we'll color the new bond, we'll color purple. Why purple? Ah, look at that. Hey. See, I can be clever. Now the hard part. Everybody see it? Realize that you still have that radical. You didn't get rid of it. What's the most likely thing this radical is going to encounter? Draw it. What's going to happen? You're going to have another radical. What's the most likely thing that radical is going to encounter? Another alkene. Draw that. Draw that. What we are now making is a polymer. Okay? This is a radical polymerization reaction. Okay? We could push it even further to a radical addition polymerization reaction. Okay? PET, let's not do PET. What's the other polymer? We could do just polyethylene. Is poly, so many ethylenes. What is ethylene? A carbon-carbon double bond. So what we've done is we took a carbon-carbon double bond and we reacted that with a whole bunch of other carbon-carbon double bonds in a polymer matrix. And what we formed is now polyethylene. Okay? There are a variety of different mechanisms for going through and making polymers. This just happens to be one of them. You're looking at the radical initiation. So if we made that look a little bit prettier, you'll notice that it looks a lot nicer when I draw it out this way. Why? Because we start to notice certain patterns when we draw these out. The polymerization is only happening within the alkene. So what I can go through and do, if I now pick this up and rotate this, because I don't like that whole right to left thing. If I run my polymer, there's one monomer, there's my OR. Oh shoot, I'm recording the silence. That's good. These chains continue, whoops, shouldn't have done that one. Those chains would then continue on forever, okay, or at least until we quenched the reaction. Okay, so we could come up with a shorthand version for drawing out our polymer system. Ultimately, what am I trying to get at with this particular reaction? I am reacting an alkene ultimately with another alkene. Okay. Why is that important? We think back to the quiz that we just took. What did we do? We reacted an alkene with another alkene. So in most of our reactions, when we think about alkene addition reactions, our alkenes act solely as nucleophiles or bases. They never really act as an electrophile. What is it acting as in this polymerization reaction? It's kind of acting as an electrophile. It's accepting electrons from another source. So given the proper circumstances, an alkene can act as both a nucleophile and an electrophile. Are those proper circumstances difficult to nail down? Yes. Right? So, if we take this a step further, we can look at our addition reactions with electrophiles. Right? And you'll notice that this is chapter 12 now in our textbook and chapter 24, so we've got those listed in their references. Okay, they all follow roughly the same basic skeleton. We take an alkene and we react it with this electrophile-nucleophile pairing. In some of the reactions, the electrophile and nucleophile are physically bound to each other. In other cases, they're separated. But in all cases, we're going through the same kind of reaction. We're putting the electrophile, or our positively charged species, on the least substituted position, and our nucleophile on the most substituted position, all the way through. Why? Why would they go to those locations? Why do I not show the possibility of putting the electrophile and the nucleophile in the other positions? Why is that not shown? Okay. You're getting too far into the mechanism. It's not substitution. We're still doing an addition reaction. Right idea in thinking about stability. What is an electrophile? It's positive. What is a nucleophile? Negative. If we look at the alkene, what would the charges most likely be on those carbons if we went through and did resonance? If we move the electrons in that pi bond, do we move them out here? Or do we move them out here? Okay. If we follow the blue, what happens to our center carbon? It becomes, and the outer carbon becomes positive. What we just said, that's negative, positive, positive, negative. That matches. But what did we just say about that matching process right here? Is that a valid product? No. We do not see the electrophile and the nucleophile match the alkene in this way. We only get this result. Why? What does our structure look like if we draw the blue resonance? What does our structure look like if we draw the red resonance? What do you want to look at, positive or negative? Positive. What makes a positive unstable? What's that? Fair enough, it is more positive. Okay. Lack of electrons. What can make it more stable? Giving it more electrons. Between these two structures, which positive is more stable? Blue or red? Red. Why? It has 2 carbons around it as opposed to the other one's 1. That means our red structure is the proper resonance structure for our alkene, or our, you may have to remind me on how we phrased this last semester, our best worst resonance structure, is that what we called it? Okay. It is a horrible resonance structure because we've got charge now in it. But it is the best of our horrible resonance structures. Okay. I don't remember exactly how we said it, but that lines it up. Which then means when I try and see how that alkene reacts with an electrophile and a nucleophile, where does the electrophile go? Electrophiles, since we know electrophiles are electron acceptors, they are what charge? Positive, which means the positive electrophile should go to the negative carbon. What's the result? It comes right out of resonance and looking at the definitions of our terms. Okay? Identifying our electrophile and nucleophile now in specific cases, it might be a separate argument, but the basics are there. The outline fits, and it matches with all of these. Okay? So, when we're looking at these new electrophiles, all of them end up generating these weird cyclic intermediates. Okay? In chapter 12, we reference 2 of them. We represent that word, a 3-membered cyclic intermediate, which I'm referring to as our tri, right? Tri, 3, should make sense. Okay? Bromine, MCPBA, diazomethane, the mercury acetate. All of those reagents end up forming three-membered transition states, or three-membered intermediates. Right? Chapter 12, we also have this four-membered intermediate, our tetra. That's with our boron reagent. When we move up into chapter 24, we end up forming these five-membered intermediates. Move up to chapter 4 even further, we end up with a six-membered intermediate in which reaction? The Diels-Alder reaction was a six-membered transition state, or intermediate. Okay? So what we're looking at is how does the alkene individually interact with some other species and what happens in that process. Okay? One of the things I tried to mark within these, albeit a little bit oddly, is our initial reactive species. So in our tri-membered, whatever's in green, and I know the A is a little bit weird there, that is the atom that's part of our three-membered transition state. When we move to the tetra, what atoms are part of our three-membered transition state? The carbons of our alkene and hydrogen and boron. When we move up to the penta, or chapter 4, what are the atoms of the transition state? The two carbons and osmium, one atom. Oxygen, second atom. Last time I counted 2 plus 2 was only 4, not 5. Where's the fifth atom? Another oxygen. You'll notice I didn't highlight the 4 because it's only 2 oxygens of the osmium tetroxide that are involved in the transition state. When we move to permanganate, what atoms are involved in it? The manganate and 2 oxygens. When we move to ozone, all 3 oxygens. Now I can highlight that 3. Okay. All of these are following the same basic principle of matching up to the alkene and generating those results. We get some crazy stuff that happens after the fact that's sort of secondary. So when we're looking at our addition reactions with the cyclo, or our tri-intermediates, we've got our alkene with its p orbitals. Those are what are reacting in the case of our alkene additions. What am I trying to show with the figure that's up here right now? What is the difference between the two paths of this reaction? They are mirror images. We're getting pretty much the exact same addition reaction through, just in different mirror planes. Why? Remember what's reacting with an alkene. Okay? It's a pi bond, which means we have electron density both above and below the plane of the molecule, which means depending on where the electrophile comes in, I have the potential for mirror images or enantiomers coming out of the product. Okay? So a lot of that dependence in our alkenes does make those reactions more difficult. All of our addition reactions will produce at least 2 products depending on the structure. For instance, what is the difference between these 2 structures? Nothing. There is no difference between them. Why? Symmetry within the molecule that makes them identical. What happens if I change one of those wedges? Right. If I change up here this structure and make this an A, okay, and the others are something else. Okay, well actually I'll have to add 2 of them, make A, B. If we propagate that through the reaction, okay, they are now mirror images of each other. So depending on the symmetry of your starting material, you may end up with enantiomers, potentially even diastereomers, or nothing. Okay? You end up with just one product. So you have to be careful on what's happening within your structure. If it's a symmetric starting material, you don't have to worry about it as much. You only have one product. If it's an asymmetric starting material, at least 2 products. Okay? Questions? The other thing I'm trying to show up here is kind of an interesting feature. If we take a look at the atom I've lined up closest to the alkene, our pi bond, what atom did I line up? Let's try letter, because it's not really an atom. What letter did I line up closest to the alkene? E, good call. I'm not trying to be tricky here. What does E represent? Electrophile. What's special about our electrophiles? It's a positive charge. How many atoms are you aware of that have a positive charge that have a lone pair? Hydrogen does not have a lone pair. That's a bit odd, okay? But in all of these addition reactions, the electrophile has a lone pair. That lone pair and the potential for it to act as an electrophile give it two functionalities. It can react with the alkene by accepting electrons, and at the same time it can donate that extra pair of electrons to the other carbon of the alkene. That other carbon of the alkene just became what when it lost electrons? Positive. What does it need? Lone pair of electrons that's coming in from our electrophilic atom. Right? How can we get an atom to have both positive charge and negative charge at the exact same time? That becomes challenging. Right? Very first one we could draw, I don't know, did I stepwise this? I did stepwise this. How does bromine satisfy this requirement? Elemental bromine satisfy this. What's the first obvious thing it satisfies? Octet. Ultimately what we're going at is lone pairs. It has the lone pair that we are referencing in this. How does it act as an electrophile? Both of those bromines are exceptionally electronegative. If we put anything near one of them, it polarizes the bond. The electrons can shuttle towards the other bromine. And we now have our active electrophilic species, which also happens to then be attached to, I think I've been showing the electrophile in blue, which is also then attached to our nucleophile, which was Br minus. Okay. So once we've formed our three-membered transition state, we now have our active intermediate. That bromine will technically be positively charged. Does bromine want to be positive? No, so it immediately starts to grab for electrons. Where does it grab for electrons from? If it grabs from the other bromide, all we do is reverse the reaction. It's not wrong, but that doesn't help us. Where else could it get electrons from? The sigma bonds that it's forming with the carbons, which means those bonds are now incredibly weak. Okay, so they start to break, but that starts to put a positive charge on the carbon, and we can't have a positive charge on the carbon because we have this three-dimensional, or this tri-cyclo intermediate. So what has to come in to support the bromine actually taking those electrons? A nucleophile on the back side of that bond to force the bromine out. Do we have a nucleophile in the case when we add just Br2? Yep, that was our bromide. That was the leftover species from our very first step. We have the nucleophile. Okay. Other reagents, our diazomethane compound. This is actually our most stable Lewis structure. Did I draw that right? Well, it's one of those. We've got a couple different resonance ones. What's special with our diazo compound? Where's our electrophile? Tricky. Nitrogen being positive. We said electrophiles are positive. Must be the nitrogen. How many electrons are around that nitrogen? 8, which means not an electrophile. It has achieved its octet. We cannot give it any more electrons. It's the carbon of all atoms. That doesn't make any sense. It's the one that's negatively charged. Why is it the electrophile? What happens if that carbon accepts more electrons? we have a phenomenal leaving group in nitrogen gas. This reaction is extremely explosive because that nitrogen leaving group is so great of a leaving group. Okay. Where's our nucleophile? It is also the carbon. Okay. And what we end up forming, instead of a final product where everything is now split open, we have a cyclopropane structure where the new carbon was that carbon. Okay, we've done our carbene reaction. Weird stuff, but that's what's going on. This next one. What's that one most commonly referred to as, particularly if I add a hint? It is not a carboxylic acid. That location can be referred to by a lowercase m. MCP B A. Meta-chloro-peroxy-benzoic acid. Will you eventually know that? Yeah. But you don't need to worry too much about it. What we've got here is this peroxy acid. Peroxy because we have oxygens bound to each other. Where's our electrophile? Or we could try where's our leaving group? Okay, where's the most reactive bond? It's our oxygen-oxygen bond. That's our most reactive one. Okay, so if we look at a leaving group of being the hydrogen, are we fixing that problem? No. So it's not a bad idea. It just unfortunately didn't work. So what we're looking at as our leaving group is either this guy or this guy. Where's our leaving group? Left or right? We have hydroxide or we have a carboxylate. The carboxylate is resonance stabilized. There's our leaving group. Which means, where's our electrophile? Our oxygen is our electrophile. The oxygen shares electrons in, we kick out the leaving group, and we go through this big mess of mechanistic arrows, and we end up forming, just as with our carbene, a three-membered product known as the epoxide. Yes. We've got the epoxide functional group. If that is all that is present, do I have a reasonable nucleophile at that stage? Nope. So the reaction stalls there until we supply a nucleophile. Last one on this list, mercury, or our mercury acetate. You'll notice that I've actually drawn things out a little bit differently. We've got the oxygens and we have AC. What does AC stand for? Acetate, good call. What does acetate look like? There you go. Right. When referring to mercury acetate, the AC is actually referring to acetyl. That is an acetyl group connected via an oxygen to the mercury. What is special about that group as a whole? This now whole group. Resonance stabilized, which means it is leaving group. Where's our our electrophile? The mercury is our electrophile. The mercury accepts electrons, and what else does it have? Lone pair. It donates electrons in. It forms our three-membered transition state. We then have to find a nucleophile, a suitable nucleophile. Okay? So far, we haven't addressed a nucleophile, so nothing happens. It stalls at that three-membered state again. Okay? All of these reagents are ultimately going the same relative transitions. Whether there's a nucleophile present or not forces certain other things to occur. So, take a swing at them. 3 minutes. So, first one, looks like most people got the bromine. So there's our basic skeleton. Do we have any stereochemistry? Yep, you're going to have to address the stereochemistry in that. What's the stereochemistry? Those bromines must be opposite sides because that three-membered transition state. They have to be drawn in trans. Because we have both ends of that p orbital, we end up getting two products out of this, so we get a pair of enantiomers. We move to that second one, a little bit trickier. Okay. Sometimes use your process of elimination. We just picked out 4 reagents. Bromine, a mercury reagent, and an epoxide reagent, the MCPBA. What was the 4th one? The diazomethane. What happened with the diazomethane? We had a really good leaving group, and we had a negative carbon. We draw that guy out. What is NaOH? Strong base. What do bases react with? Hydrogens. What happens now? There's our really good leaving group. We get our cyclopropyl structure again. Do we have stereochemistry? Yes. Enantiomer? No. Diastereomers, because that stereochemistry did not change in the course of the reaction. Okay, so the relationship between our products ends up being diastereomers. The mercury one. We form our mercuronium intermediate, and we have to look for that nucleophile. Is there a nucleophile listed here? Water is our nucleophile, causes that structure to bust open, and what we will end up with is our OH and our mercury acetate out there. Last one with our MCPBA, we form our epoxide. Since our oxygen are forming at the exact same instant, we do not change the orientation of our double bond. So if it starts trans, which it is, our final product must show trans as well. Okay? Of these, were some of these really tricky? Yep. That's why you practice. Okay? And you may have noticed with the mercury one, how often do we see mercury bound to carbon? Not very often. In general, it's a bad thing to see happening. Hence, we have something referred to as mercury poisoning. When mercury forms a bond to carbon, it is a relatively strong bond. It is not particularly easy to break. Okay? To force that bond to break open, we end up using hydride to force that mercury off. Okay? The only way we can stabilize the hydride as a strong nucleophile is to attach it to another atom that is willing to somewhat share those electrons temporarily, but is happy enough to let the electrons go. The only atom that will do that is boron, and that is kind of where we're stopping today. I might record a quick 5 to 10 minute lecture to finish out our boron stuff, because it's ultimately review. And I'd like to start moving into new material for the rest of the semester, as opposed to keep going back. Okay? So you can expect a review lecture to show up on the rest of Chapter 12. We'll pick up on Monday with Chapter 24 with our penta intermediates. So that's our osmium tetroxide, our potassium permanganate, and our ozone. Those will be for Monday. Okay?